Welcome to This Explainer. Today, we are digging into Shattering the Uncuttable, the detective story of the atom. It's a story that perfectly proves science isn't just some dusty, static collection of facts. Actually, it is a continuous, completely thrilling process of breaking old rules. We're looking at the atom today, and how generations of brilliant minds systematically dismantled literally everything we thought we knew about the universe. It's the ultimate question, isn't it? What is everything actually made of? You, me, the device you're using right now, the stars up in the sky. If you zoom in close enough, what do you actually see? For centuries, the smartest people on Earth thought they had the final, indisputable answer to this fundamental mystery. They were absolutely convinced they had found the absolute bottom line of reality. But, as we're about to see, the universe loves a good plot twist. All right, Section 1, the uncuttable box. Let's take a look at the baseline theory of matter. Okay, let's dive into this. To really appreciate the breakthroughs of modern chemistry, we first have to dismantle the mental box that scientists and philosophers lived in for thousands of years. Just think about the massive gap in time here. Around 400 BCE, the Greek philosopher Democritus proposed that if you cut matter down far enough, you'd eventually hit these tiny indivisible particles. He called them atoms, which literally translates to uncuttable. It was this revolutionary philosophical concept, but it had zero experimental evidence. Incredibly, it just sat there as a philosophy for over 2,000 years. It wasn't until 1808 that English scientist John Dalton finally proposed the first actual scientific atomic theory. Dalton essentially gave the scientific community a checklist, a strict set of established rules for how matter works. He stated that matter is composed of extremely small atoms. Crucially, he insisted these atoms absolutely cannot be divided, created, or destroyed. He also noted that all atoms of a specific element are perfectly identical in mass and properties, and that compounds form when these uncuttable blocks combine in simple, whole number ratios. It was neat, it was tidy, and well, these are exactly the rules our scientific detectives are about to completely break. Moving on to Section 2, Cracking the Box. This is where we hit our first major anomaly. So fast forward to the late 19th century. Technology advances and the first major crack in Dalton's uncuttable theory appears. And the weapon that cracked the atom? It wasn't a hammer, it was a glass tube. Scientists like Thomson use what's called a cathode ray discharge tube. If you've ever seen an old glowing neon sign or one of those really bulky early tube TVs, you're looking at very similar technology. You seal a gas at low pressure inside a glass tube, place a negative electrode, a cathode, on one end, and a positive electrode, anode, on the other. Apply a massive jolt of electricity, and suddenly these glowing rays shoot from the negative side to the positive side. But what exactly were they? Thomson dug into this and found some incredible evidence. The rays moved in perfectly straight lines and produced fluorescence on the glass. But here is the genius part. When exposed to electric fields, the rays deflected toward the positive plate. The logic here is simple but totally profound. Because opposites attract, these mysterious rays had to be negatively charged. Thomson even calculated their specific charge-to-mass ratio, finding it to be an incredibly precise 1.7588 times 10 to the 11th power coulombs per kilogram. So the crucial takeaway here is this. The rays weren't just energy. They were actual physical particles. Thomson had just discovered the electron, and in doing so, he delivered a massive twist to the scientific world. The uncuttable box was officially cracked. Atoms are not the smallest things in the universe. They are absolutely divisible, and they contain even smaller, negatively charged pieces. But, of course, this discovery created a brand new problem. We know atoms are overall electrically neutral, right? So if they contain negative electrons, there has to be something positive balancing them out. Thomson proposed what we now call the plum pudding model. He suggested the atom is a positively charged sphere with these newly discovered negative electrons embedded inside it, kind of like plums baked into a pudding. It was the best guess they had at the time, but it definitely set the stage for the next great mystery. Section 3, Weighing the Ghost. Let's figure out the mass of this new electron. Okay, so Thomson found the charge-to-mass ratio, but the actual individual charge and mass of a single electron, that remained a total mystery. Figuring out the weight of this invisible ghost particle was the next massive hurdle. Enter Robert Millikan in 1909, armed with, honestly, one of the most elegant problem-solving methods in the history of science, the oil drop experiment. Millikan literally sprayed tiny oil droplets between two electrically charged metal plates.
By incredibly carefully adjusting the voltage, he could perfectly balance the downward pull of gravity with the upward push of the electrical force. He was literally suspending oil in midair to measure the impossible, the charge of a single electron attached to those tiny drops. And get this, he found it.
The exact electrical charge of a single electron is negative 1.602 times 10 to the negative 19th coulombs. That is an unimaginably tiny decimal. Just pause for a second and think about the sheer precision required to measure something so infinitesimal using essentially a perfume atomizer, some oil, and a microscope. No way, right? Now, what's really interesting about this slide is how Millikan took that tiny charge and combined it with Thomson's earlier charge-to-mass ratio. With those two puzzle pieces, he calculated the actual mass of a single electron, 9.109 times 10 to the negative 31st kilograms. This wasn't just a win for chemistry. It provided one of the most accurate measurements in the entire field of physics at the time. Section 4, the positives and the neutrals. It's time to balance the atom. All right, so we found the negative pieces, but if atoms are neutral overall, there must be something positive to balance the books. When scientists tweaked those gas discharge tubes we talked about earlier, they noticed something else. While cathode rays were shooting toward the positive plate, there were entirely different rays, called canal rays or anode rays, moving in the exact opposite direction. Because these canal rays deflected toward the negative plate, scientists knew immediately they had to consist of positively charged particles. This discovery immediately sparked the next huge breakthrough. By testing a bunch of different gases, they found that the absolute lightest positively charged particle came from hydrogen. They named it the proton. And what's amazing here is that the proton carries the exact same amount of electrical charge as the electron, positive 1.602 times 10 to the negative 19th coulombs, but its mass is 1.672 times 10 to the negative 27th kilograms. So it is significantly heavier than the electron, but it perfectly balances out its charge. So we have electrons and protons. Case closed, right? We're done. Actually, not even close. There was still this massive suspense building in the scientific community because of a glaring missing mass problem. If you added up the weight of the protons and electrons in an atom, it simply didn't match the actual total mass of the atom. The math was wrong. Finally, in 1932, James Chadwick solved the puzzle. He directed alpha particles at a piece of beryllium and detected a highly penetrating, entirely neutral radiation coming right off it. Chadwick had found the final piece of the puzzle, the neutron. It's a subatomic particle that carries significant mass, almost identical to the proton at 1.675 times 10 to the negative 27th kilograms, but it has absolutely zero charge. This discovery was a real game changer. It finally explained the missing mass, solved the weird mystery of isotopes, and unlocked the secrets of nuclear stability. And that brings us to Section 5, the complete subatomic picture, the final blueprint. We finally pulled all these historical threads together, from an ancient Greek philosophical idea to a complete, measured, and verified blueprint of matter, and this brilliantly illustrates exactly where we landed. We have a clear map of the three fundamental subatomic particles. You have the incredibly light, negatively charged electron orbiting outside the nucleus. You have the much heavier, positively charged proton sitting right in the center, and joining it in the nucleus is the neutron, providing essential mass and stability with zero charge. Now, you might be wondering, why should you even care about these impossibly small numbers? Why does this invisible world actually matter to your everyday life? Well, because this microscopic blueprint explains literally everything. The movement of electrons explains every single chemical reaction there is keeping your body alive right now. The protons determine the properties of all elements on the periodic table. Our grasp of this structure is the very foundation of modern technology. It's exactly why we have electrical conductivity and the semiconductors powering the smartphone or computer you're using to listen to this. It unlocked nuclear energy. It explained radioactivity. It completely transformed chemistry from a guessing game into a predictive, world-changing discipline. We went from Democritus in ancient Greece imagining a tiny, unbreakable ball to a complex, buzzing, dynamic system of quantum mechanics. And it really makes you wonder, if the atom, the literal definition of the uncuttable, was actually hiding an entire universe of complexity inside it, what other invisible universes might be hiding right in the palm of your hand, just waiting for the right detective to look a little closer. Thanks for joining me on this explainer. Keep questioning everything.